Hello, in this video we're going to take a look at indefinite integrals where this plus c thing comes from, as well as some interesting antiderivatives. A reminder of our definite integrals is when we have a start and an end of our integral, but an indefinite integral takes a look at the antiderivative of an entire function. This does not find the area underneath a curve, it just undoes that operation of finding the derivative. Gets us back to the original function. We just apply our power rule in reverse. We add 1 to our exponent, and then instead of multiply, we divide by our new exponent, not the original exponent that we started with. And then for these indefinite integrals, we apply this plus c. This plus c comes from if there was a number at the end, and we had done the derivative of that number, we would have just gotten that 0. So the act of finding the derivative gets rid of our constants. So we need to reapply that constant by adding this c. We can apply this process ourselves. Right now I have that big quotient being divided by x to the fourth, so it's going to be easier for me to find my integration by dividing all of those numbers. So this is going to be the integral of x to the fourth divided by x to the fourth, so that's just a 1, minus 3x to the negative 2 when we divide that x squared by x to the fourth, plus 5x to the negative 4. I just want to try to make all of these negative exponents because that's going to be easier to apply my reverse power rule. So when I integrate, I have an x to the 0 on this first term. I add 1 to that exponent, making it just a regular x, and then divide by my new exponent, which is 1, which doesn't really do anything. So, but I'm going to write it anyway, just so you can see that I did it. Minus 3x, I'm going to add 1 to that negative 2 exponent to make it a negative 1, and then divide this by my new exponent, negative 1, then plus 5x to the negative 3 now, over my new exponent, which is negative 3. Now that I am done, I still need that constant of integration. I need to add on that plus c. Now, that was all a bit of a mess because I'm kind of writing out all my thoughts, and I don't necessarily want to write it in a neat format. I just want to clean this up so it's a little bit easier to look at. So those two negatives make a positive. We get 3 over x plus minus 5/3 with that x cubed in the denominator, and then we get this plus c. I don't know what that c is. It could be any number of things, but this is going to be equal to my original integration. Sometimes we're given an initial condition which we can use to determine the value of c that we got from the indefinite integral. So here I got a second derivative. I wanted to figure out what the original function was. I found the antiderivative, which was x cubed over 3 plus c, and now I want to know what is that c value. So we can say 8 equals 0 cubed over 3 plus c, which gives us a neat little equation that we can solve, and we find that c equals 8. So we can rewrite our derivative now that we know what c is as x cubed over 3 plus 8. That was the value that got turned into a 0 when we found the second derivative. We can go one step further in this problem to find what's going on with the original function. So just do that antiderivative again. The original function is going to be the antiderivative of x cubed over 3 plus 8. Applying our power rule, we get x to the 4 over 3 times 4 plus 8, and we get a new x on that 8, plus a new c that we're going to have to track down. Let's plug in the value that we got up here, this f of 0 equals 4. So that'll tell us that 4 equals 0 to the 4th over 3 times 4, I can do that, that's 12, plus 8 times 0 plus c. Well, that's going to be 0, and that's going to be 0, so, oh, cool, c is just going to equal 4. Now we can write our original function. F of x is going to be x to the 4th over 12 plus 8x plus 4. If we weren't given those initial conditions, we're not able to figure out what that c value could be. Sometimes we get in trouble, like Mel is right now, and we need some alternative tricks in order to figure out what our antiderivative is. Just like derivatives, not everybody can use the power rule. The particular ones that a particular one that we care about is this one right here. This will get you out of trouble, just like Mel just got out of trouble. And let's take a look at an example of why this thing does what it does. What I'm about to do is wrong. I should be applying one of those rules we just had on the screen, but I'm not. I'm going to try to use the power rule on this. So I would have the antiderivative of 5x to the negative 1 dx. And if I apply my power rule, I would add 1 to that exponent, and I would get 5 x to the 0 over 0 plus c. Well, I can't divide by 0. So since I can't divide by 0, it seems like I can't find the antiderivative of this thing. But I can if I follow my proper rules. Back when we were working with derivatives, if we had a natural logarithm, that was one of the ones that also did not follow our proper rules. And I remember, hey, when I did the derivative of natural log, I got 1 over what was going on the inside. So what we can do is, since we've got a constant in there, we can take that 5 out, and really we're working with the antiderivative of 1 over x dx. The derivative of ln of x was 1 over x, so the antiderivative of 1 over x must be the ln of x. But since this is an indefinite integral, I need to tack on that plus c. Note that that 5 was just chilling in front, so it keeps chilling in front. Now, this one's a bit of a mess. I don't want that dx up in the numerator. I want that separated from the rest of it. So I want a fraction, and I want 1 over dx. Now, looking at that denominator, I think that's just a couple things squared. That's 3 squared minus x squared, which, if I think back to, and I got it hidden right here, that's like my arc thingies. Now, these aren't commonly tested, but it is still nice to see them because you never know what's going to pop up. I can tell this one is not arctangent because it doesn't have that square root. There's no square root in this one. So it must be this arcsine function. So my a value is going to be that first thing that's being squared, the positive thing. So that's 3. And the u is going to be just that x. So this is going to equal the arcsine of u, which is x, over whatever my a value is, which in this case is 3. This is an indefinite integral, so I need to do this plus c. This same trick, if this was a definite integral, would work. You just wouldn't have that plus c, and you would be able to do that top minus bottom. That's the end of this video on our indefinite integral. Don't forget that plus c. It's really easy to forget that plus c. And if we're given an initial condition, we can use that in order to figure out what is that value of c. I've given you a couple of weird rules. The major one you want to make sure you've got memorized, but you kind of have already in terms of derivatives, is this natural log. These ones are important to know, which you also have kind of memorized a little bit already from when we were doing derivatives, but they don't show up too often on the AP exam. But it's something you want to be prepared for if you're looking for that 5. Thanks for watching, and see you next time. Bye-bye.